Okay, so in this video we're going to explore the concepts of open balls, closed balls and spheres in a function space. So the function space we're going to consider is, the underlying set is going to be equal to the set of continuous functions defined on the closed interval 0, 1. So to draw a picture of that, we have the interval 0 to 1 here in the real line. So this is 0 and this is 1, and we are looking at the set containing absolutely every single function which is continuous on this line. Now remember, theories from real analysis tell us that continuous functions on a closed bounded interval like this obtain their maximum and minimum and are therefore bounded. So these functions are quite nice. So this is the set. This is the set containing all functions which map the interval 0, 1 onto the real line such that, f is bounded. F is continuous. F is continuous rather than bounded. That would be a different set. That would be the set B0, 1 rather than C0, 1. Okay, B is continuous. So of course we know that all the elements C0, 1 are in fact, this entire set is contained within the set of bounded functions on 0, 1 because of that theorem from real analysis that says that all continuous functions are bounded on this interval, and in fact that they obtain their maximum and minimum. Okay, so that's just a set. To turn it into a metric space, we need a metric defined on this. So we're going to define the distance between two functions f and g to be equal to the supremum over x as an element of 0, 1 of the modulus of f of x minus g of x. Okay, so let's just make sure that that is a metric space. Because let's firstly make sure that this distance function is defined. Because f and g are continuous, it implies that f of x minus g of x is also continuous. Now, if a function f is continuous, so let's have a look. Let's just draw a picture here. If we have a function, let's say something like this, on some interval, let's just complete it so it's like there. So 0 to 1, let's say, and we have some function like this which is continuous. Then if you take its modulus, so this is, let's call this f of x minus g of x. Then if you take its modulus, in fact, let's draw it in the same thing here. If you take its modulus, all that you do is this bit above 0 stays the same. It's the bit that's below 0 that flips. So it's going to go something like that. And so it's going to flip this negative bit into the positive axis. But the point is that when you take the modulus, so when you take this new function, which is the modulus of f of x minus g of x, it will still be continuous, providing the thing that you were taking the modulus of is continuous. Then f of x minus g of x, the modulus of that will also be continuous. So the point is that mod of f of x minus g of x is continuous. Okay, that implies that on the interval 0 to 1, it implies that on the interval 0 to 1, mod f of x minus g of x is bounded and obtains its maximum and minimum because it's a continuous function on this closed interval, is bounded and obtains maximum and minimum. Obtains its maximum and minimum. And in particular, what we're interested in is what is the maximum of it. We're interested in the supremum. So this supremum exists basically, and indeed you could actually replace that with the maximum of x as an element of 0, 1, because it's not just the supremum of the function. It's the actual maximum of it because it is actually obtained. So the difference between the maximum and minimum is if you take the supremum of some set. Let's say, let me give you an example. So if I take the set of all points, all elements of the real number, so x is an element of the real number, such that x is less than 1, then that set looks like, if this is the real line, then you go up to 1, but it does not include 1. It converges up to 1 and gets as close as you like to 1, but it never actually gets to 1. The supremum of that set is equal to 1. Supremum of this set x is an element of the real numbers such that x is less than 1 is in fact equal to 1. So because 1 is the least upper bound of this set. If you take any number lower than 1, then I will be able, so if you take any number to the left of 1, let's call this h, then I will always be able to find you a number bigger than h, between h and 1, which is going to also be less than 1, such that it will be in this set, which will mean that h will not be a supremum. So any number to the left of h cannot be a supremum, and obviously 1 is an upper bound for this set, so it's greater than or equal to any element of this set, so it therefore must be the supremum, because I've proven to you that if you take any number less than it, it's no longer an upper bound, basically. So 1 must be the least upper bound. But it's not the maximum, because the set doesn't actually contain 1. If I took the set x is an element of the real numbers such that x is less than or equal to 1, then the set actually now contains 1. The supremum of this set is still equal to 1, because if I take any, now if I draw this again, I go up to 1, and I have, in that set, I have every element up to 1 and including 1. Then if I take any element bigger than 1, then there's always exists another element, but so let's say this is h, then there will always exist another element between them that is less than it, which will contradict this, which is still an upper bound. So there exists another element in here which is less than it, which is still an upper bound, so it would contradict h being a least upper bound. So no element greater than 1 can be a least upper bound. And you might think that it's a bit odd, because 1 isn't bigger than itself, so how can it be an upper bound? But the definition of upper bound is that you are greater than or equal to every single set, every single element in this set. So 1 is a good least upper bound in this case. And in this case, you can say that this is actually equal to the maximum of this set. X is an element of the real numbers. X is greater than or equal to 1. And note, this set has no maximum. There is no element in here which is biggest. Give me any element getting as close to 1 as you like, that you think is biggest. I will always be able to find you another element bigger than that, that's still less than 1, basically. Just take the, if you have, say, some element, let's say little y, which is an element of this set, so let's say it's somewhere here, then I can just take the mean of y plus x divided by 2, so the average of them, and I'll get some number in between them, which is still less than 1, so it's still an element of the set, but it's greater than y, so it will contradict y being the maximum. So this has no maximum, whereas this set does have a maximum. And in this case, you could have a set, you could have a function that converges up to a value but then never gets to it, whereas this theorem from real analysis says that if it converges on anything, it will actually get there. So basically, there does exist a maximum. There is a number there is a number in this codomain which is a maximum for that. Okay. So this is well defined, basically. This will ascribe to every single function, or every single pair of functions, f and g, which are an element of c, 0, 1, a number. So let's just remind ourselves of why this satisfies the axioms of a metric space, and then we'll explore the concept of open balls, closed balls, and spheres. Okay, so 1. The distance function between f and g needs to be a positive, non-negative real number, so it needs to be between 0 and infinity. Okay, well that's obvious because because if you look at the definition, the distance between f and g is equal to the supremum over x as an element of 0, 1 of the modulus of f of x minus g of x. This function is always non-negative. Therefore, when we take its supremum, we're going to end up with a non-negative function, non-negative value. The worst possible scenario is that this function is identically 0 everywhere, in which case the supremum is equal to 0. But it is certainly non-negative, so it's always going to be an element of the non-negative real numbers. Okay. Second, the distance between a function and itself, we need to make sure that that is equal to 0. Okay. Well, the distance between the function and itself is equal to the supremum x is an element of 0, 1. Of the modulus of f of x minus f of x. Now, if I take a function f and I subtract it from itself, then at every value of x in 0, 1, this is just going to equal the real number 0. So the modulus of 0 is still going to be 0. So we're going to be taking the supremum of a set which is 0. So it's going to be 0 over the entire interval 0, 1. So we're going to be taking the supremum of a function that is identically equal to 0, so this is just equal to 0. Conversely, we have to make sure that if the distance between f and g is equal to 0, that implies that f is equal to g. So if the distance between f and g is equal to 0, then that implies that the supremum over x is an element of the interval 0 to 1 of the modulus of f of x minus g of x is equal to 0. Now, this is a set that we are taking the supremum of. This says that for every if this supremum is equal to 0, then that says that for every value x is between 0 and 1, the value of the modulus of f of x minus g of x must be equal to 0, because it cannot be negative, it has to be non-negative, but if any value was greater than 0, it would contradict this being the supremum being 0. So for all x is an element of 0, 1, the modulus of f of x minus g of x must equal 0. So that holds for all x is an element of 0, 1. Okay, so now we'll come on to the other side of this paper. So now what we get is, so this is what we've got so far, that the modulus of f of x minus g of x is equal to 0 for all x is an element of the interval 0 to 1. Okay, so that implies that for all x is an element of 0 to 1, that since the modulus is only equal to 0 if the thing that you're taking the modulus of is itself 0, it implies that f of x minus g of x is equal to 0, which implies that for all x is an element of 0, 1, f of x is equal to g of x, which implies that the function f is actually equal to g on the entire interval 0 to 1. Okay, so third axiom of a metric space, that the distance between f and g is equal to the distance between g and f. Well, the distance between f and g by definition is the supremum as x is an element of 0 to 1 of the modulus of f of x minus g of x. And basically this modulus sign doesn't care if we take f of x minus g of x or g of x minus f of x. So this is just the supremum x is an element of 0, 1 of the modulus of g of x minus f of x. Okay, and that is just equal to the distance between g and f. Okay, brilliant. So we get symmetry. Fourth property, the triangle inequality. If we take h, another element of C0, 1, then the distance between f and g is equal to the supremum as x is over x is an element of 0 to 1 of the modulus of f of x minus g of x. Then basically, this is exactly the same as the supremum x is an element of 0, 1 of the modulus of f of x minus h of x plus h of x minus g of x. And then basically what we can say is, using this same inequality again, that the modulus of a plus b is less than or equal to the modulus of a plus the modulus of b, we can say that this is the supremum, well, that we can say that it's less than or equal to the supremum x is an element of 0, 1 of the modulus of f of x minus h of x plus h of x minus g of x. Okay, so we've just split this up in here, viewing a as being f of x minus h of x and b as being h of x minus g of x, and this is then equal to the supremum over x is an element of 0, 1 of the modulus of f of x minus h of x plus the supremum x is an element of 0, 1 of the modulus of h of x minus g of x. Okay, and this is just the definition of the distance between f and h, and this is the distance between h and g. So we get, therefore, that the distance between f and g is less than or equal to the distance between f and h plus the distance between h and g. Okay, so now that we've just had a bit of a recap of why that set of continuous functions between 0 and 1 emits this metric and forms a nice metric space, let's now study the open balls, closed balls, and spheres in this metric space. So let's take some function f, which is an element of C0, 1, and let's have a look at what the open ball of around centered at this function f of radius, let's just say radius 1 is equal to. In fact, we'll generalize it. Let's say the radius r, where r is some number greater than 0. So basically, if we draw a picture, we have our closed interval 0 to 1 here, and we have some function f, which is between 0 and 1 like that. Okay, and basically, we're now saying this ball or centre to f of radius r is going to be equal to the set of all functions that say g is an element of C01 such that the distance between f and g is less than or equal to r, but the distance is defined to be the supremum as x is an element of 0 to 1 of the modulus of f minus g, and we want that to be less than or less than r rather, because it's an open ball at the moment, less than r. So we want the maximum distance between f and g to be less than r, where we are viewing this as the modulus. So basically what we want, I'm going to show you what we want, and then I will justify exactly why this is the case. What we want is, this is the set of all functions such that they are contained within this ribbon around this function here. So basically, if you draw this ribbon like that, and then there are dashed lines, but it's quite difficult to see, I think, on the camera. But this ribbon, at every single point, so take a little point x, this ribbon has height going downwards, r, and height going upwards, r. So you basically draw this ribbon around this function f at the centre. So this effectively, this top bit is f plus r, and this bottom bit is f minus r, and basically this set here contains any function which exists within this ribbon. So here is an example of a function which exists within that ribbon. Any function which is just within that ribbon, basically, is going to be within the set. And the reason is that the distance between any function that's within this ribbon and the function f is going to be less than r, because if we take the modulus of f minus g, then it will be equal to, if we look at this specific example here, so if we have the 0, 1, and we want to plot out what is, firstly we'll just plot out what is f minus g. So f minus g, here what we have is f, and g originally is bigger than f, so we're going to get something going negative like that. Then at this point here, f is now bigger than g, so we'll get something going positive. Then we'll go down again, up again for a little bit, and then down, and then we'll stay down like that. So this is our f minus g. Now if we take the modulus of that, we'll get something that looks like this. Like that. And providing it was within the ribbon, the maximum of this modulus minus f minus g, so the maximum of it must be less than r, because it cannot possibly get further away from the function f than r if it was contained within this ribbon, because every single, if you look at what g of x was, then it's always going to be within the ribbon r. So g of x minus f of x, f of x minus g of x, if you take the modulus of that, it's always going to be less than r, because it's within this ribbon, and this ribbon goes up to f plus r and f minus r. So if the value of g of x is within the ribbon, then it must be less than f plus r, but greater than f minus r. So its modulus must in turn be less than r, and that's for all x as an element of 0, 1. So when we take the supremum over x as an element of 0, 1, we cannot possibly get a value that is greater than r. So greater than or equal to r, in fact. The reason being that, again, this is going to be a continuous function. If f is a continuous function and g is a continuous function, which they are, then this modulus of them is also going to be a continuous function, so it will obtain its maximum and minimum. So you can't have one of these silly supremums where it's converging on equaling r. It will actually obtain its maximum and minimum. So it cannot have a supremum equal to r, because if it did have a supremum equal to r, its maximum would be equal to r, and if its maximum was equal to r, then at some point the value of g would actually be on this ribbon, and I've said no, you have to actually be within the ribbon. So we can say even that the supremum is strictly less than r. So any function that is contained within this ribbon, it cannot be on the boundary points, it must be strictly contained within the ribbon, is going to be in this ball of radius r around f. So that's what open balls look like in this metric space. Okay, so now what we want is to look at closed balls. Okay, so similar to in this example, if we want the closed ball of functions f around r, with b tilde rather, this is equal to the set of functions g, which is an element of C01, such that, again, this supremum x is an element of 0 to 1 of modulus of f minus g is less than or equal to r. So this time, if we have a function f defined on the interval 0 to 1 here, then all these functions g which are in this ball, we want to be within a ribbon. So again, I'll draw a ribbon, but this time they can actually equal the boundary point. So this is the ribbon. This upper function is f plus the value r, and this middle function is obviously f, and this lower boundary for the ribbon is f minus r. And basically, now what you can have is you can have functions which actually touch that ribbon, and maybe in multiple places. They don't have to touch it in multiple places, but they can touch it. They can touch it whenever, but they don't have to touch it either. It contains all functions that don't touch it either. So it's any function that is contained within the ribbon, and it can actually touch the boundary points. Okay, so in that case, the maximum value of f minus g is indeed going to be less than or equal to r, because if you actually touch this the boundary point, then of course your maximum modulus will be equal to r. If you don't touch it at any point, then your maximum modulus will be less than r. Okay, and then finally let's have a look at the sphere centre of f of radius r. Okay, so we have some function f, and now what we want is we want all the points. So we want the set of all g as an element of C01, where the distance between f and g is actually equal to 1. So the supremum of the modulus of f minus g over x as an element of 0, 1 is actually equal to r. Now, if we draw the ribbon again, so like here, this function here in the middle is f, this upper function is f plus r, this is the function f minus r. We want the maximum value of the modulus of f minus g to actually be equal to r. Therefore, any function that is going to be in this sphere, in this set, at some point, it has to have modulus. It has to have the modulus of its distance between f to equal r. So at some point, it has to either touch the upper boundary of the ribbon, or it has to touch the lower boundary of the ribbon. It can't go out of the ribbon. It must not go out of the ribbon. It must not go out of the ribbon, because if it went out of the ribbon, the maximum distance of f minus g would be something else. But it must at least one point touch the boundary of the ribbon. So every function in here must at some point touch the boundary of the ribbon, and it can touch either the bottom boundary or the upper boundary, or it can touch both, and it can touch them multiple times. It must not leave the ribbon, but it must touch the boundary, because you do want the maximum value of the modulus of f minus g to equal r. So at some point, the modulus of f minus g must equal r, which means at some point it must touch this ribbon. But it must also stay within the ribbon, because if you go outside of the ribbon, then your modulus will be greater than r away from f, and then your supremum would be something different from r. Okay, so that is the concept of open balls, closed balls, and spheres in function spaces. In the next video, we'll go on to discuss concepts of open and closed sets.